Hello, my friends. Welcome to Origins. My name is Don Chapman. It's my privilege to be your host, and it's great to have you with us today. You know, Origins is a forum where we take the evidence of science and we use it to validate the truth of creation. We have Dr. Danny Faulkner with us today. So good to have you with us, Dr. Faulkner. We're going to talk today about craters. I know there's craters on the moon. Are craters unique to the moon?
No, they're not. We find them in a lot of places.
Lots of places. They have some real significance for us.
Yeah, you know, for a long time, I must confess, the moon I found was kind of boring. I was excited back in high school when we were going to the moon with the Apollo program, then I lost interest. But in recent years, I've come back to think about the moon quite a bit. And I've come to realize that the moon has a lot of things to tell us about the history of our Earth, perhaps, and the solar system in general.
Wow. Well, I'm still not that excited, so I'm really excited to learn from you what you know that I don't that will help me appreciate the moon.
I'm going to show you some photos of different things in the solar system. You mentioned the moon, so I'm going to start with that. And when you think of the moon, if I said, well, think of the moon, what would you think of?
Saturday night date.
No, come on. Think science.
Well, I think how it gets full and
But what do you think about on the moon? What kind of features? Craters, right?
Craters on the moon. You see those all the time.
And you can see here on the edge of the moon here, all sorts of craters showing up. They show up best along this division between night and day. We call it the terminator. That's where the shadows are longest,
right,
and cast a nice shadow. So the moon has lots of craters, and a good question, a couple of good questions would be, well, where do craters come from? And why does the moon have so many? And do we find them other places? Would be another question we can ask.
Okay.
And when you start doing that, we get some real interesting hints about some histories. It's neat to be alive right now because we've been in the space age now for several decades. We've sent space probes to all the planets, and we've photographed many of the satellites, some of the asteroids, and we now have a lot of information to draw upon to make some general conclusion about these bodies. This may look like the moon to a lot of people. In fact, I sometimes will ask, I'd ask you, but you probably fall in the trap. This is actually the surface of Mercury.
Oh.
And what do you notice on Mercury?
You see the craters.
You see craters. Now, I look at it, and the craters look a little different. The density's different. The depth's different. It's one of those things that there's some subtle differences between lunar craters and Mercurian craters. But there's still craters there. So maybe, just maybe, craters on Mercury came from the same place that craters on the moon came from. Now, the next planet out from the sun is, of course, Venus. And Venus is surrounded by a thick atmosphere with thick clouds. We can't really see the surface, but we can penetrate it with radar. We've done that with a couple of spacecraft and made nice maps and a lot of studies of the surface of Venus. And here we have a very large impact crater. Right here is the impact crater with an ejecta blanket around it. The ejecta blanket is a debris field that's blown out when a crater forms. The appearance of a crater tells us a lot. If it's worn out, kind of rounded down, that suggests it's kind of old. And if it's real sharp looking, that suggests it's sort of young.
Sure.
And so we've can make some conclusion. But we find craters on Venus, not nearly as many as we find on Mercury or on the moon. We still find a fair number of craters on Venus as well. And here we have a photograph of Mars, and you can see a number of craters on the surface. Here's one. There's a big one right here. I like that crater, don't you?
Yes, sir. A little smiley face.
A little smiley face down there on the crater. That's a funny little crater. But Mars has lots of craters too. There's a large area on Mars that's heavily cratered and an area that's not quite as cratered. Here we have an asteroid. And you can tell it's an asteroid, well, because it's not spherical. Planets are spherical and asteroids generally aren't. I can't remember the name of this one. I think it may be Ida. But what do you see? Well, you see craters again, don't you? Here's a crater right there.
There are really some big ones.
Big ones right here.
Is that a big crater on top?
That might be, but this is definitely a crater. You've got craters all over the place, and it's an odd shape, kind of potato shape. So again, we keep seeing this theme. Now, the next few questions I ask you, what do you see? The answer is going to be craters. Okay, that's what we're looking for.
Help
you out here a little bit. Okay, now be careful in this one because this is Io, the innermost large moon of Jupiter, and it doesn't have any craters.
No craters on that one?
No, not at all. But look at the surface. This is one of my favorite moons.
I think I see pepperoni.
Yeah, it looks like pizza. You can see cheese and pepperoni. There's a nice piece of look like an olive right there, I think. But nice tomato sauce and cheese.
But no craters on that one.
No craters. Now that's interesting because did it get missed or somehow did it not get craters to start with? Well, in the Voyager space probe in 1979, we went past, saw this interesting surface. We also caught something else. We can see here on the edge of Io this little blue thing sticking out over the edge of the planet. Here's a magnification of it. That's a volcanic plume. It has volcanoes on it. In fact, here are two photographs. Same area. This is the same area of Io taken about a year or two apart.
I see.
Look how different they are.
Yeah.
And it's because volcanic activity. You know, in the Voyager probe in '79, they saw as many as 24 volcanoes erupting simultaneously.
Wow, just while they were flying by.
Just while flying by. So it's the most volcanically active body in the solar system, more active than the Earth is.
So I'm going to assume that it's not that they didn't receive craters, it's that that's filling themselves in? Is that...
You really are a good scientist, Don.
No, I'm not. But
that's exactly what's going on, we think.
Yeah.
We had craters, but they were filled in. And so if a surface is very active, either by weathering or by geological activity with plates moving or glaciers or erosion of various things and volcanic eruptions, you can cover over old craters.
Craters are pretty universal unless something happens to make them
Unless
go
something
away.
renews the surface and changes it.
Okay.
Okay, this is the second large moon of Jupiter. This is Europa, and it's an icy covered satellite, and it has a few craters on it. You can't see them here very well, but not very many. But here's one. Here's a close-up, and you can see a large crater right there on the surface. These are cracks and fractures in the ice surface of Europa. Now, the fact that Io has no craters and Europa has a few, that tells us that Europa's been less geologically active than Io has. Okay. But certainly more geologically active than, say, the Moon or Mercury. The key here is the more craters you see, the more density of craters, probably the less active, and hence probably the older the surface that you're looking at.
Oh, okay.
So it turns out we think the surface number of craters tells us the relative ages, not absolute ages, but relative ages. This is the next big satellite of Jupiter. It's called Ganymede, and all these little white dots you see on here, you got dots all over the place on this thing. Those are all impact craters. Ganymede has more craters than Europa does. So what's going on there? Less geologically active. Probably the surface on Ganymede is older than the surface on Europa, and the surface on Europa is older than Io. That's pretty obvious to me. Now, the evolutionists and the creationists are going to disagree about how those absolute ages fall out. I'm going to put it in thousands of years or even less. I'm going to put it over millions or billions of years. But I think we can agree the relative ages on these things.
Okay.
Let's see, here's another one. This is one of my other favorite satellites. This is Mimas. It's a medium-sized satellite of Saturn. I like this one because it's covered with impact craters, but look at this big one right here.
Isn't that something?
You know, it reminds me of the Death Star from the Star Wars movies. This big beam comes out, and destroys a whole planet. So it makes you kind of wonder, doesn't it? But that's why I like this satellite. It's got a huge impact crater. That large crater is called Herschel. And by the way, trying to describe how Herschel came about, that's a real trick because it's such a large impact. This is another neat moon. What does it look like?
A cantaloupe.
Looks like a cantaloupe. You're absolutely right. Everybody agrees on that. This is Triton. It's one of the large satellites, I think, of Neptune. And it's got a surface over here. The cantaloupe portion has a few craters on it. You can see a few up close. They're kind of small. And it's been reworked a bit. And over here you have some other surface. We have some craters on the surface of Triton, some indicating reworking, some not less reworking. Where we see more craters, it seems to be geologically less active and hence an older surface every time we do that. Now, can you tell me what body this crater's on?
Well, I'm looking at that. It looks like a road in the building, so I'm going to guess that's on Earth.
Very good. In fact, this is in Arizona. This is called the Arizona Meteor Crater. This thing happened a few thousand years ago. They used to say millions. Now they're saying 50,000. But Indian legends talk about this thing falling out of the sky.
Is that right?
You have much more recent than that. The diameter of this crater is about a mile across, and it's about 600 feet deep. Now, you know, I've been to Meteor Crater twice, been to Grand Canyon several times. The first time I went to Grand Canyon in Arizona Meteor Crater was around 1997, I believe. And I went to Grand Canyon. It's about what I expected. It's big, it's grand, it's beautiful. But here in this visitor center here, it's a big place. It doesn't look big on the photo, I know, taken from the air here. But when you go through the museum, you step around the corner and your first view is through a plate glass window, huge view of it. It literally took my breath away. I gasped. You could put every NFL stadium on the bottom and still have room for some parking. It's big, unbelievably big. And we think it's similar to the craters we find on some of the other bodies we've talked about here. Here's to prove I was there. This is me with one of my astronomy buddies. We went out there, and you have to pay a few bucks to get in, but you can stand on the rim here. And again, it's 600 feet lower than us down there. So, huge place. By the way, these little green dots you see over here, Those are good-sized cedar trees, as are these.
Oh, those are trees. Okay.
Yeah, cedar trees. They're big, actually. So it's quite a deal. All right, where do craters come from? Well, we see craters on nearly every solid surface in the solar system, including the Earth, the Moon. The only thing we don't see it on is Io, and we already explained why we don't get it there. And where do the craters come from? Well, another question is, did God make these craters? Is He responsible for them somehow? Did He make those? And we can answer those questions. Hopefully we can ask those questions in terms of that third question there. Well, there are two basic theories of where craters come from. One is that they perhaps are volcanic. Volcanoes produce craters many different ways. You have a caldera at the top of a volcano, but you can have what are called fumaroles and other fissures that open up and leave a crater behind. And that was a very popular theory throughout the 19th century and well into the 20th century. The other theory is that impacts, those large bodies come in, asteroids, and come in and boom, when they hit, they explode and open up a huge area. Incidentally, the thing that the impacting body is far smaller than the crater. The Arizona crater, a mile across, 600 feet deep, probably 150 feet across, the thing that came in. Huh. But it's moving like 40 miles per second.
The impact just is so
It's
massive.
the energy that's released when it hits. It's sort of like an artillery shell, can be this big around and leave a 30-foot crater. It's explosive power.
Yeah, that's a good, if you think of a bomb hitting and how big
explosive reaction coming there. So that's really important. And so today we think that most of the craters are probably impacts. Okay. And there is some holdout. Some of them we do think a few smaller ones on these bodies may be actually volcanic related. But the point I can make is we can infer a history here. Old surfaces generally have many craters, as I've pointed out. Younger surfaces will have few craters because of the weathering or other processes that will wear those things out. And so no matter if you're an evolutionist or a creationist, we can infer a history out of all this. That's what's very important. We can infer a history out of this. And what we can establish are relative ages, not absolute ages. That information has to come from some other source, through your assumptions or other things. So the paradigm we have is that high crater density comes from greater age, and low, we can also look at overlaps of craters. If a crater overtops another one, you can tell it's an older crater, younger crater, and get the order of appearance there. Sure. And so we can use this, look at the sharpness morphology, how worn down are they, because with time they do wear down a little bit. So we can use all of those tools to develop some sort of history.
All right, well, that's very fascinating. I'm anxious to see where all this is leading. I just need to see the implications of it, and I'm sure you're wondering too, what are the implications of craters? We're going to find that out as soon as we come back. We're taking a break right now. Don't go away. We'll be back real soon.
Creation versus evolution. You weigh the evidence. Mercury's magnetism. Amazing activity. The space probe Mariner 10 studied the magnetic field of the planet Mercury in 1974 and 1975. Based on the assumption the solar system is 5 billion years old, scientists assumed that Mercury would have come to equilibrium and lost all its magnetic field. To their amazement, scientists discovered that Mercury's magnetic field is still very active. If only thousands of years old, it's no mystery why Mercury would still have a measurable magnetic field. No other explanation exists. Today's guest on Origins, Dr. Danny Faulkner, is also the author of Universe by Design, an explanation of cosmology and creation. This is an excellent book for upper-level homeschool curriculum or the library of an astronomer. Orders are being taken at 1-877-CRS-BOOK. Dr. Faulkner has a degree in math, his master's in physics, and a PhD in astronomy from Indiana University. He is full professor at the University of South Carolina, Lancaster, where he teaches physics and astronomy. For more information about our guest, you can write to Dr. Danny Faulkner, 1402 University Drive, Lancaster, South Carolina, 29720. Or send him an email.
We're back, and I'm here with Dr. Danny Faulkner, and we're talking about craters today and what they have to teach us about creation. And Dr. Faulkner, you have the crater there in Arizona up on the screen. That crater was made by a meteorite hitting. Have they found the meteorite?
They tried to look in the bottom in a couple of places. I understand many years ago they did a drilling right there at the bottom. The earlier photograph I showed you, there's some white dust sitting there. That's the tailings
As
from
a
it.
layman, I would assume it hit dead center.
Yeah. And then they thought for a while it maybe came in at an angle like this and might have been buried beneath the surface over here. So they did some drilling over here along the edge of the crater. Went down thousands of feet, found nothing. But what they found over the years is around the ejecta blanket, out for miles, there are fragments of this thing, the thing that came in. Most of these types of meteorites we find are about 90% iron. And so as they took a truck with electromagnet under the bottom, drove across the desert, it just sucked up tons of this stuff. I have a piece of the Canyon Diablo, they call it. It's about the size of my little finger. And it's very heavy, about 2.5 times heavier than you think it ought to weigh, because it's made mostly out of iron and nickel. But that's an interesting point. We think it blew up in the air, and it was the explosion that actually, the air that actually excavated.
This is the impact from the explosion in the air that caused it to...
On the moon, it would have hit directly and been buried, but on the Earth, it's going to hit the atmosphere.
Because of the atmosphere, it's burning up. And it burned up just before it got
It didn't burn up, it pancaked, actually, and then exploded.
Bam. Okay.
Well, here we have a photograph of the moon. Now, the moon is interesting because it keeps one face towards the Earth all the time. It rotates and revolves at the same time. So we only see the front side of the moon. The back side we never see. In fact, we didn't see until 1959 when this first spacecraft went behind the moon and photographed it. And there's some interesting things there to mention. But you'll notice that the moon, this is taken near full phase. There are two different types of features on the moon. There are these darker areas right here. All right, these are darker areas, and we have then the lighter areas up here and down there, dark and light. And it kind of gives the man on the moon appearance. We say in the West, other countries it's a rabbit in the moon or other things like this. But it's an interesting feature. And notice that there are a lot of craters up here in these light-colored areas, a lot of craters here, but very few craters in these darker areas. And notice also the shape that they have. Round, round, round. They all kind of overlap a bunch of things here. So the circular shape is very interesting. And we can use that to kind of infer a history about the moon. But we have the two types of terrain showing up there nicely. So what are those two types of terrain? Well, the one type, the lighter region, is called the highlands. And the highlands are lighter in color, as we've written there. Also, it's less dense. Why do we know it's less dense? Well, because it lies at a higher elevation. It's higher up, highest regions on the moon, hence the name highlands. And furthermore, it's heavily cratered. Now, you tell me, if it's heavily cratered, what does that tell you? It's an older surface, hasn't been reworked geologically. But the other surface we call the Maria. It looks like Maria, but it's Maria. That's Latin, and it's plural for seas. The singular is mare, M-A-R-E, not mare as in Old Gray, but in mare as in Latin. They were called those by Galileo 400 years ago when he first looked at the moon through the telescope, because he thought that being dark and smooth, they might be bodies of water. Indeed, they are darker. They're denser because they lie at a lower elevation, and they're less cratered, which tells you what? They're
younger.
Younger, all right. And also that round shape is interesting. You know, I don't know if you noticed it, but when you look at those mare, the Maria, they look like large craters in a way. And it's exactly what we think that they are. And the reason why they're darker is because this is made out of a type of rock we call basalt. It's a real dark volcanic rock, and the lighter highlands are made out of a lighter colored rock we call granite. Not doing a very good job of drawing that, but it's granite. And granite is a light colored rock, and basalt is a dark colored rock.
It's made out of different substances.
Different types of rock. And you know, we inferred that before the Apollo program. They brought back the rocks from the highlands and the Mare, and guess what? It matched what we inferred.
We have rocks from both here on Earth now.
And they confirm what we already figured out. That's a good example of how subtle science can be in trying to figure things out. Well, this is an image of the entire moon. It's a map, more or less, taken with a lot of some spacecraft. It's distorted up near the poles, so you know how Greenland looks huge on a map? These craters up here and down here aren't nearly as big. And what's interesting is the following. This part right here, roughly, that's the front side of the moon. That's the side we always see. And this part over here matches up over here in this part. And that's the back side of the moon that we don't see. Do you know something interesting?
The front is the darker and the sides are the lighter.
Yeah, notice the front side is got about 50-50 mixture of Maria and highlands.
Right.
But notice that the backside is almost entirely highlands.
Okay.
That's interesting that you have it on one side but not on the other. Okay. And I think that's important when interpreting the history of the moon. The front side, 50-50 mixture of highlands and Maria. Back side, about 95% highlands. So it's very different, the front and the back side of the moon. I would have never figured that out to be the case if I was predicting this before we actually went and saw the back side of the moon. Okay, when did the craters form? That's a good question. Let's think biblically now. Let's don't think like evolutionists. Let's think biblically. And there's several possibilities. One at the time of creation. And I don't think God just shaped these things. I think He actually had something come in and hit the surfaces to do this. So it might have happened on the creation, the fourth day, when the moon and the other objects were made, perhaps assembly of these things. Could have happened at the time of the fall. There were things that happened across the world when the fall happened in the Garden of Eden. And then we have the flood. That's another catastrophe. Could have happened at that time. Some people suggest other times of judgment and catastrophe. I'm not a very good fan of that. And it could be a combination of those. In fact, I have warmed up to the idea in recent times that a large part of the craters perhaps come from the time of creation, and there's maybe a second episode of cratering at the time of the flood. And so since that time, we've had maybe occasional cratering, not much.
Right here or something like
Every now and then.
Yes.
Okay, so that's my sort of idea. So let's discuss my proposal for lunar history, a little different from what the evolutionists may have, mainly in difference in time scales. Because I'm going to do it in a short period of time, years or months even, as opposed to billions or millions of years. Okay, my proposal is this. The moon surface, notice it has two episodes. The Maria and the highlands seems to suggest two different episodes of things going
really
on.
Clear.
Yeah,
Two whole different things.
and on one side. And I think that most of the highlands date from the time of the creation. On the fourth day, God made the moon, uses the word a saw there, which is translated made, not create. I think it indicates a process, a rapid one, directed, miraculous, but still it wasn't instantaneous ex nihilo creation. He took material he'd already made on day one and shaped the moon, and perhaps those craters in the highlands were evidence of the last few bits of material coming in and hitting the lunar surface. And then you have those large impacts I told you about, the big round things that look like, we call them the Maria.
Yes.
We call those impact basins. And we think what happened there is a huge body came in, blew out a massive crater, cracked the surface very deeply, and when it did, it allowed molten material to come up from inside and flood over that, thus covering up all the craters there and starting all over again.
That would explain why it's a whole different substance. It came from
inside. And it explains why it's round, why it's dark, why there are few craters on it. It explains everything very beautifully. And the question is, why did that happen only on one side of the moon and the other? Well, the flood happened very briefly. And I'm thinking that since the moon takes a month to rotate around once like this, if you had a swarm of things that come in and hit the moon on one side, you're not going to hit the back side of the moon if it's happened in less than, say, 2 weeks. Why would it come and hit the moon? Well, I think maybe at the time of the flood, the Earth was the intended target. And they say in military terms, the moon was collateral damage.
I see.
Got hit because it happened to be close to the Earth at that time. And the volcanic overflow came up immediately and flowed over and filled those up. And since then, very few craters.
Now,
and
you're not saying God missed.
No. He sent a swarm of projectiles, and I think maybe he had to trigger the moon, the flood. It had something to do with the flood because we have evidence of impact craters that happened during the flood.
Okay.
And that's interesting. So I think the Earth was hit as an intended target, and the moon being orbiting next to the Earth was unfortunately hit at the same time. And we don't see this segregation so much in impacts anywhere else in the solar system.
That's fascinating. Truly, truly fascinating. It's a fascinating world out there, isn't it?
Yes, it is.
There's going to be craters in the earth. You're going to feel like there's some craters in your life sometimes. But when you know the God of peace that passes all understanding, that's all you need to know. Remember, my friend, it's God's view that He created you. That should be your worldview too. Trust Him. Until I meet you again here on Origins next time, God be with you, my friend.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file of program number 903 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins, program number 903, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.